Okay, our guest lecturer today is soon to be Dr. Panca Jodiawan. He's currently a PhD candidate from National Taiwan University of Science and Technology, or Taiwan Tech, and basically he is coming from the same lab with me, so I guess if you see some similarity regarding our publication, our research fields, yeah, that's because we have the same teacher. Okay, so I guess I would not really introduce too much. I will let the times for today's sessions more for Dr. Panca to share about his topics and discussion today. Okay, please, Dr. Panca, the
Thank
session is
you.
yours.
Thank you, Dr. Wira. Okay, so I will share my screen first.
Sure. Let me add you as the co-host. Sorry.
Okay.
Okay. I think now you can share the screen.
Okay. Okay, so could everyone see my screen now?
Yes, very much
Okay.
clear.
Okay, thank you, Dr. Wira. So thank you everyone who attend today's webinar. And the topic that I would like to present today is the application of adaptive large neighborhood search for solving vehicle routing problem and its variants. My full name is Panca Jodiawan, and you may call me Panca. And as Dr. Wira has told you earlier, that I am from the same lab as Dr. Wira. So the name of our lab is Global Logistics and Supply Chain Management Laboratory in National Taiwan University of Science and Technology. I would like to briefly introduce myself. So for the education part, I almost complete my PhD in industrial management from 2019 up to now in NTUST. And then I finished my master also in the same department, in the same lab in 2019. And the earliest one is I got my Bachelor of Engineering in Industrial Engineering in 2016. And for the upcoming position, I hope that I could start in August 2022. I will become a postdoctoral fellow in the same lab, and I will be supervised by Professor Vincent. And the research area of me includes these three big topics: logistics optimization, meta-heuristic or Matheuristics. Okay, so I will start with the outlines of my presentation. So first, I will present about the capacitated vehicle routing problem. This is one of the most famous combinatorial problem in the logistics. And since the adaptive large neighborhood search that I will discuss soon, it is firstly applied to solve a variant of vehicle routing problem. So I think it's worth to study or to learn about the capacitated vehicle routing problem. Then after discussing about the CVRP or capacitated vehicle routing problem, then we'll move to adaptive large neighborhood search. And I have dissected the sections into several points here. I will start with highlights and then the main framework, that destroy and repair operators. Then I will continue to the acceptance criteria. And then the adaptive weight adjustments. I will show the demo, short demo of the C++ code. And then lastly, I will share some tips and tricks for developing the state-of-the-art adaptive large neighborhood search. Okay, so let's start. Now, the first session, the capacitated vehicle routing problem. I'll start with the problem definition. Hopefully that some of you have ever heard of this name, but okay, let's start with the definition. First, let's consider there is one depot the depot is the term for the source of goods. Okay, and then in a given planning period, you have a set of customers. So you could see there are several customers existing with different locations, and they are noted by C, so it's the customer. And here we have maybe 16 customers in total. And then the number above, okay, let me see. Okay, the number above the figure, it represents the demand. Okay, it's the number of the demand of that customer. Could sorry for the interruption. Could you see my pointer on the slide?
Yeah, it's color in red, right?
Okay,
yeah.
Yes. Thank you, Dr. Wira. And then the next one. Oh, okay. So the capacity of the, now here we have a set of vehicles, except that those vehicles will depart from the source of the good, the depot. And here we have, for example, 3 trucks or 3 delivery vans, and the maximum capacity of each delivery van is 70. Okay, so I put some numbers here, and then the question is how to serve the customers, the given customers here, of a given planning period with an objective of minimizing the total distance traveled by the delivery vans. Okay, so I summarized the capacitated vehicle routing problem definition into this equation. Then the next one, let's see. After I will give you a solution illustration for the problem. Let's say this is the first route. It starts from C14 and then ends at C4 before returning to the depot. And then the second one is it starts from C13 and then it will ends at C3 before returning to the depot. And for sure, the constraint of the CVRP that the solution need to fulfill is that the capacity, the total demands that can be carried by a delivery van. Let's say here we utilize 2 delivery vans, right? So for each delivery van, the maximum capacity, that the maximum demand that can be carried is 70. So you could start to calculate or take the summation of each demand here, like 8 plus 7. Let me use the pointer. Like 8 plus 7, 13, 4, 6, 10, and 2. Then it shouldn't be greater than 70. The same for the second route. 5 plus 4 plus 7 plus 10, 3, 12, 19, 8, and 2. When you take the summation of all of them, then the number shouldn't be greater than 70. And this is the summary of the routes. The first route is 0, 14, 6, 10, 11, 1, 9, 4, 0. 0 represents the depot, the source of the good. And then the second route, it represents the second delivery vans, starting from 0, 13, 2, 12, 8, 5, 15, 7, 16, 3, and it ends at 0. Now, considering the routes that have been created before in the previous slide, I would like to talk about the solution representation. This part is very important because later when you develop a meta-heuristic, not only adaptive large neighborhood search, but maybe also other meta-heuristics, you always need to design the solution representation in the beginning. Then the solution representation will determine with some good solution representations will cut the computational time of the heuristic that you design. So basically, what I have ever seen so far, there are 2 types of solution representation. The first one, or the first option, is It is represented in a single dimensional array, okay, or a single dimensional list. And here, considering these two routes, and then we try to put it into the one-dimensional array. Then we start with the first route 0, 14, 6, 10, 11, 1, 9, 4, 0. That is the first route. And then we continue with the second route 13, 2, 12, 8, 5, 15, 7, 6, 16, 3, 0. And what is the last zero? What does the last zero mean? Since we have 3 delivery fans in our problem definition earlier, if you notice that we have 3 pictures of delivery fans on the right hand side, that's the last zero. It means the unemployed delivery fan or the unemployed truck. We still consider that because later, maybe instead of 2, the meta heuristic will use 3 delivery fans in a particular iteration. Okay, but in the beginning here, since we only have 2 routes, so we only have let's say here we have 2 routes, and then the last one, the last 01, we just directly put it in the end of the solution representation. Then the next one is the 2-dimensional array or the 2-dimensional list, the 2-dimensional factors. It depends on what programming language do you use, but here is the main difference. You could see that each row, okay, each row, it represents the index of the vehicle. So the first vehicle, then you just need to put in the customers visited by the first delivery fan. So as well as the second route. Then the third route, since the third delivery fan is not used, then we just put 0, 0. It means that it is there is no route, or it is an empty route. Okay, so these 2 solution representations are the solution representation that I have ever seen. Then before we move further to the adaptive large neighborhood search, let's have some short exercise, and I hope that you could give some put your questions. Okay, write down your question in the chat. I would like to see your answer. Let's start with the first one. Okay. So the first one, in the CVRP, or Capacitated Vehicle Routing problem, every customer can be visited at any time point within the given planning period. Is that true or false? Okay, Thank you, Dr. Vera. Is that true or false? There's no true, I think. Yes, okay. Thank you. How to call your name? Dang, or I hope I pronounce it correct. Thank you, Dang. So that is correct, that the answer is every customer can be visited at any time point within the given planning period. We are talking about capacitated vehicle routing problem without time windows or without the range of time that the customer is available. So you can visit every customer at any time point within the given planning period. Then the second one is each truck must be fully loaded before departing from the depot in capacitated vehicle routing problem. Is that true or false? Okay, thank you, Mr. Greg, for the answer. But actually, it's false. Okay, so each truck shouldn't be fully loaded before departing from the depot. Okay, it can be partially loaded. It can be less than, we call it less than full truckload. Okay, so in CVRP, we do not assume that each truck must be fully loaded before departing from the truck. But thank you for the attempt. Please keep try to answer. And I think there will be no point deduction if it is wrong, right, Dr. Vira? Yeah, okay. So just keep giving your answer, okay? The third one, try to remember the, okay, thank you. Thank you, Dr. Artin. Yes, all trucks must be utilized is false. Thank
It's
you,
Dr.
Srinivas.
Yogi, actually.
Oh! Hello, Dr. Yogi. Okay, thank you. So all the trucks must not be utilized as it is illustrated in the previous solution. We only utilize 2 instead of 3 vehicles. Then each truck can only have 1 single trip. Is it true or false? Oh, okay, thank you, Dr. Yogi. Dr. Ape. Okay, oh.
That one is Dr. Artfin, sorry.
Okay, so each truck can only have 1 single trip. It's true because we are talking about capacitated vehicle routing problem, CVRP, and there is another variant called multi-trip vehicle routing problem, and in that case, this statement is false. But for the basic CVRP, this statement is correct because, yeah, we assume that each truck can only have 1 single trip. Okay, so those are the short exercises for the CVRP. I hope it can make the problem assumptions of CVRP clearer. Then we move to the adaptive large neighborhood search, and I would like to present some highlights or summary about the first development of adaptive large neighborhood search. Okay, let's talk with the who found or who invent the adaptive large neighborhood search. The adaptive large neighborhood search, or abbreviated by ALNS. So from now on, I will use ALNS to represent the adaptive large neighborhood search. So ALNS was developed by 2 well-known professors. I'm a big fan of them for sure. Professor Stefan Ropke and Professor David Pissinger. Both of them are the professors in Technical University of Denmark, and they invented or they developed this algorithm in 2006. And since the adaptive large neighborhood search, it is firstly developed to deal with VRP variant. And we know that VRP is a very difficult problem to solve. So here, ALNS cannot make sure that you can obtain the optimal solutions, but if it is well designed, then you can obtain the high quality solutions. Therefore, ALNS belongs to the class of metaheuristics. Maybe you have ever heard some classical metaheuristics like simulated annealing, genetic algorithm, particle swarm optimization, etc. So those the ALNS belongs to the same class with them. Then the third one, the first problem, okay? The first problem tackled by the ALNS is pick up and delivery problem with time windows. This is a variant of vehicle routing problem. And then the fourth one, since the success of, since the many researchers have seen the excellence of ALNS, a lot of researchers have tried to develop their own ALNS to solve many problems in several application areas. And I have put the references in the end of the presentation. Maybe later you could see the name of this paper, Mara et al. In 2022. There are several of application areas such as manufacturing system, healthcare, farming, etc. Then now we move on the pseudocode. So do not be afraid of the pseudocode. I will not explain like line by line, but I will just show you the terms first, okay? We will learn more and more later. So just first, do not take a look on the left-hand side, just take a look on the right-hand side, see the symbol and the description, okay? So the S here, we have a lot of S, okay? We have a lot of S represent The original S, it represents the initial solution or the current solution. The S accent, it represents the working solution, and the S star, it represents the best known solution so far. Okay, so please take care of these three. Please remember these three terms in the beginning. And the fourth one is the F. Okay, the F means the objective value. Ignore the other parts because we will come back to those later. Okay, just first remember the first four terms: S accent, S star, and the F. Okay. Now, the framework or the pseudocode, this pseudocode is also obtained from Mara et al. 2022 for your information, so you could check it out later. And the framework is basically divided into two phases. The first phase is the initialization phase. So you need to initialize several parameters, and of course, you need to start with a solution. Okay. The solution means the set of the routes, okay? The routes that you have seen in the beginning in the CVRP, we call it a solution, okay? So we initialize a solution, we initialize the parameters required by the adaptive large neighborhood search. You do not need to know first the parameters list, but here what you need to know is we start with an initialization phase. Then the remaining part is the main phase of the adaptive large neighborhood search. Let's see, for the main phase, we categorize it into several parts or several steps. We start with the destroy and repair operators, okay? We will discuss this later. And after that, after applying the destroy and repair operators, then we move to the acceptance criteria. We apply the acceptance criteria. We need to know whether the new solution created by the destroy and operator should it be accepted or not. Then we have a term called adaptive weights adjustment, and that what makes the adaptive large neighborhood search special in one of the reason. Okay, that's why they call it adaptive. Okay, because they have adaptive weights adjustment. And then okay, that's all. Frequently asked question. I will come back to the questions maybe after. Okay, maybe I will go to the question first because it's another section. How to implement ALNS if I cannot do programming? Wow, such a challenging. Thank you, Dr. Vira, for the question. So far as I know, I haven't seen any black box of ALNS, not like I know that maybe Python have provided like GA, SA, they have provided black box, and then you can just adjust the parameters and you fit in the problem and you can get the solution. So in that case, you still need the programming, but very little programming skill. But for ALNS, so far, unfortunately, I haven't seen any black box of ALNS. Is the sequence like neural network? Because we keep updating the weights until we reach the threshold. Okay. Thank you for the question, Dr. Artvin. I have learned a bit about the neural network, and as I remember, you do the forward to calculate the target value, and then based on the target value, you calculate the error measurement, something like MSE, and then you use those error values to update the threshold, right? So it means that you update the threshold every iteration. However, in the adaptive large neighborhood search, a little bit different because you will not update the weights every iteration. It will be updated periodically. But later I will explain the how to update the what is that, the adaptive weight adjustments. Okay. Okay, you're welcome. And one more thing, we do not have any threshold in adaptive large neighborhood search. Okay. So before applying the destroy and repair operators, we need to determine how many customers do we need to remove from the S accent. Okay. So you have seen the complete solution is the set of the routes. Okay. Then before you apply those operators that we will discuss soon, we first need to determine how many customers you want to remove from the solution. Okay, and you need to apply this this formulation. The row here, it represents the number of customers to be removed, and it is bounded two sides, lower bound and upper bound. And the lower bound and upper bound themselves belong to the set of integers. Okay, they cannot be continuous, but so far I haven't seen continuous values. Okay, so let's say this is 4 and then this is 10. So it means that you can remove the customers in between 4 and 10. Okay. Then now, since we have a set of destroy and repair operators, okay, now you can imagine that in destroy operators, you do not only have one destroy operator, you have a set of destroy operators and also a set of repair operators. The principle of selecting the destroy and repair operators in one iteration follows this rule. Okay, so I think most of you or some of you have ever seen this in genetic algorithm. We call it ruled wheel. But in the genetic algorithm, we know that the ruled wheel will be used to select the which individuals need to be selected. But here we use the ruled wheel to select the destroy and repair operators. Okay, so please take a note on the difference between the adaptive large neighborhood search and genetic algorithm. In adaptive large neighborhood search algorithm, we use the ruled wheel to select the destroy and repair operators. And maybe there's another question. What is the probability of selecting each destroy and repair operator? In the beginning, we set it equally likely. Okay, so if you have 5, for example, you have 5 destroy operators, then each destroy operator will have 0.2 probability to be selected. Okay, because the summation of the probability should be 1. So that's the short introduction for the principle of selecting the destroy and repair operators. And here, since the first development of ALNS, I have told you that there are a lot of researchers have been developing their own versions, their own ALNS versions. And here is the overview of the common destroy operators. You have a lot here: random removal, worst removal, shear removal, etc. And I will not discuss all of them. Okay, I will not discuss all of them, but I select the first 3 since they are originally proposed in the paper of Professor Robke and Pissinger in 2006. So let's start with the random removal. Okay, so the name has represented the mechanism of the removal. Random removal means you will randomly select the customers and then you will remove them from the solution. Let's say the mechanism now randomly select, and then you will get C12 and then C5 and then C10. Okay, then this is the first the route, right? From the complete route that I haven't the complete route, it has not been destroyed by the random removal, so the customers are still complete in the routes. Then after you remove those 3 customers, you will see that the routes will become shorter for sure. Then what will happen with the question marks? You will delete the links, and then you will simply connect the customer before and the customer after the node. Okay, so you remember that there is a node here, and then you just delete the link, and then you can reconnect the previous node and the after the following node. Okay, C8 and C15, and you will do the same with the other removed nodes. Okay, and here we have removed customer 7, customer 12, customer 5, and customer 10. Okay, and you the resulting solution, let me see, this is the result of applying the random removal. Okay, it's not a complete solution. So the output of the destroy operator, every destroy operator, not only random removal, is a partial solution. We call it partial because some of the customers are taken out and we need to repair them later, okay, by using a set of repair operators. So remember, this is the clear output of the destroy operator is a partial solution. Okay, the partial solution here, it only consists a subset of customers, not a complete set of customers for CVRP. Then the next one, we move to the show removal. Okay, that's all for the random removal. We just randomly remove the customers and take them out from the solution, and it will become the partial solution. Now we move to the show removal. Show removal is quite a unique name because actually show removal is originally invented by someone called Shaw, and because maybe like decades ago they like to name what they invent by their names, right? So we call it show removal until now. Okay, again, I will use this example again and again, so please stay tuned with the example. We have exactly the same example here. Then I would like to introduce you with a new term. In show removal, there is something called relatedness measure, okay? Or it will be abbreviated by RIJ, okay? Since you want to measure relatedness, okay, you need at least two nodes or two customers in this case. That's why it is represented by I and J, okay, to measure the similarity between two customers in CVRP. Okay, how do we measure the similarity in this case? Okay, so specific, I could say that relatedness measure, it depends on the problem that you faced. That's why here I write down RIJ for CVRP, because the RIJ for, let's say, the problem tackled by the first ALNS is totally different with this one. Okay, so what I write down here, it is specifically for CVRP. So the RIJ is calculated by taking the summation of DIJ plus DJI. DIJ means the D here is the distance. Okay, so DIJ means the distance from customer I to customer J plus the distance from the customer J to customer I. Then let's take an example here. To measure the RC1, C9, it means that you need to calculate the distance from C1 to C9 plus the distance between C9 to C1. Okay, so that is the how do you measure the relatedness or the similarity in CVRP. Now we move to the algorithm. Do not need to pay attention too much to the algorithm part, but I will explain it as clear as possible. Okay, the first one is okay, you need to select one customer randomly. Okay, you can imagine that in the previous slide you have a lot of customers. Okay, you have a lot of customers, and to start the algorithm you need to choose one customer randomly. Okay, that will be the seed customer, and you need to take it out and put it in the list D. Okay, D means the list of the customers that you have removed. Okay, that's the first phase. Select one customer randomly as the seed customers. Then what will you do next? From the list of the D, okay, from the list of the D, then you will select that just one request or one customer there. And after that, you will calculate the relatedness measure here, the relatedness measure, and sort the list of customers which are not in the D. The name of the list is L. Let me take a look. Let us take a look back here. Now let's say that in the first iteration, you take C1 as the seed of the customer. Okay, C1 as the seed of the customers. Since you have 16 customers in the solution, It means that the remaining customers that you need to calculate the similarity or the relatedness measures are in total 15 customers from C2 to C6 then. So you need to measure the similarity between C1 to C2, C1, C3, C1, C4, and so forth. Okay, and after you get the values, then you will put it in the list and you sort it. Okay, you sort it and you sort it in the let me see, it should be okay. They do not they have said here that it should be it should start from the smallest one to the largest one. That means that you need to sort it in a way that you keep the most similar one in the top of the list and the least similar one in the last in the last part of the list. So we sort it in that way. And after you do the sorting, then the last phase is to put the selected customer in D. Okay, so after you sort the list, then you will choose using the line 9 here. Okay, and then you will get the customer, the selected customer, and then you will put it in the D. Okay, that's how the show removal works. Okay, then we move to the worst removal now. The worst removal here, it is quite similar with show removal. Okay, but instead of similarity, there is another measurement that we call the removal cost. Okay, in the show removal, they pay attention to the similarity, but in the worst removal, you need to pay attention to the removal cost. And here we define a new term called cost IS equals to the objective value of the S minus the objective value of the S when the component I is excluded from the S. For example, okay, for example, here you have, we want to measure the removal cost of C1. Okay, and we are still talking about CVRP. Okay, the whole example will be about the CVRP to make a simpler explanation. And take a look, the cost C1 in the solution equals to Fs minus F minus C1 S. Then how to calculate the removal cost? It's just like you calculate the total distance from the C11 to C1, C1 to C9. Okay, and then minus the direct distance from C11 to C9. That is the removal cost of C1. Okay, that is the example for how we calculate the removal cost in the CVRP. And then again, if you have understood this part, how to calculate the removal cost, then we just need to do the iteration. First, we need to calculate the removal cost of each customer. You see that we have 16 customers in the example. Then you need to calculate it one by one. How much is the removal cost of each customer? Then you will select the customer to be removed. Okay. We will talk. Don't worry about this part, the line 5, because you have already seen it in the show removal, right? But we will have a short exercise how to calculate it. Then after you select the customer, then the third one is to remove the selected customer from the solution. Okay, so the 3-phase will iterate until the number of customers to be removed have been fulfilled. You calculate the removal cost of each customer, which still inside the solution, and then you will select one of the customer based on the criterion defined in the line 5. And then after you select the customer, then finally you will remove the selected customer from the solution. You will do it again and again until Q. Q is the number of the solutions to be removed in this case. Okay, so let's have some exercises again. Then the number of the customers removed in each iteration may be different, true or false. So in just like the meta heuristic, you do not only have one iteration, you have a lot of iterations. And in each iteration of the ALNS, the number of customers may be different, true or false. Okay, yes, that's correct, Dr. Yogi, Dr. Artvin. So that's correct that the number of customers removed in each iteration, it could be different. I use may because sometimes you can generate the random number, which is the same with the number of customers removed in the previous iteration. So since it's completely random, we do not know whether the generated or the new random number is the same with the previous one or not.
Dr.
And
Yogi left the chat because this is not human factors. It's too far. This is Dr. Artvin, you know. Sorry, Dr. Panca. Bye-bye.
bye-bye, Dr. Yogi, Professor Yogi. Okay, so the second one is the second one, a worse. This is not a true or false question. So please pay attention because we want to learn more how to remove a customer from the list. Okay, so a worse destroy operator is implemented and there are 4 customers left in the solution. Okay, and then we have calculated the removal cost. I believe that you have got the idea of calculating the removal cost of each customer. Okay, so let's see. This is the remaining customers, C2, C5, C7, and C10. Okay, and then the removal cost is 20, 15, 45, and 25. And I will recall these lines in algorithm 3. Okay, so starts with the array. This is all planned requests or all planned customers sorted by the descending cost. Okay, you have here, okay, sort it first by in a descending manner. Okay, you can take a paper or you can calculate it in mind. Then the fourth one, choose a random number in the interval 0 to 1. Okay, then it means the code will generate a random number between 0 to 1. And then the selected request, pay attention here, the selected request R equals to the index. We need to select the index of the list. Okay, yeah, the index of the list. Y is the random number. Remember, Y is the random number powered by the P. Okay, P is the parameter. Okay, later I will give you the value of Y and P in the exercise, and multiplied by the cardinality of L. The cardinality of L is how many customers remain in the L. Here we have 4 customers. It means that the cardinality of L is 4. Okay. So by considering this information, let Y equals to 0 and P equals to 3, which customer will be selected by the worst destroy operator? Oh, thank you, Dr. Wira. That is the list that has been sorted, I believe. Yeah, yes, yeah. So for all the participants, the L provided by Dr. Wira is already, yeah, that's correct, because we need to sort it descendingly. Yeah. So given, by considering the given list and provided information here, Y and P, which customer? Just have a try. Don't worry. Don't worry to make a mistake. C5. I see. Okay. Okay, thank you for the answer, Mr. Andrew. So let's calculate the R. The R is the R equals to L, and then we calculate the operation there. We need to take the power, the 0 powered by the 3 is 0, and then we multiply 0 by 4, it's also 0. So it means that we need to take the request L0. And how to see the L0, please pay attention to the list given by Dr. Rira. L equals to C7, C10, C2, and C5. L0 is the first one. Okay, L0 is the first one. So that means what the customer that you need to select is C7. Yep, that's right. That's right, Dr. Artin. It should be the C7. Okay. Thank you for the answer. So is there any question regarding the destroy operators? We have learned about the worst, with the simplest removal, random removal, and then we have what else? Shell removal, and then worst removals. Considering these 3 removals, do you have further questions?
Dr. Pancha,
Yes.
how do you set the value for Y and P?
Y and P. Okay. So thank you for the question, Dr. Artfin. For the Y, it is generated randomly by the code we call the random generator. For the P, we need to use the parameter tuning to tune the P. Yeah, so it's the parameter of ALNS that needs to be tuned.
Okay, thank you very much.
You're welcome. Okay. If the other participants have other questions, please let me know either by the chat or you can directly turn on the mic. And then now we move to the repair operators. Okay, so now we still I put the table of an overview of the common repair operators from the same paper. Then here listed a lot of some of the repair operators. And greedy, do you have? No, I don't have pancha, remove, and repair operators. Thank you for the question, Dr. Wira. Then now let's take a look on the table. We have greedy insertion, and then we have K regret, random insertion, sequential, cluster insertion. Again, I will just discuss the first 2 insertions, the greedy and the regret insertions, since they are originally proposed by Professor Rocky and Pissingers. Then let's see from the basic greedy heuristics. Okay, I think maybe some of you have ever heard about greedy. Okay, greedy algorithm. It's a simple construction heuristic, and it is used as one of the repair operators in the original ALNS. And there is a new guy here called delta FIP. Okay, the delta FIP denote the change in the objective value caused by the insertion of the customer I into the position P. It's a very long sentence, but soon I will show you the illustration. So following the greedy approach, we need to obtain the following information. Okay, it is written mathematically, but what we want to say here, it means that in every iteration, we need to find the insertion position, okay, the insertion position that results in the least cost. Okay, so you need to find the least cost position of the customer. And since we have a lot of customers to be inserted, let's say you have removed in using the removal operator, you do not only remove one customer, right? In the end of the removal operator, maybe you remove 4 customers. Then by considering each of these 4 customers, which customer that results in the least cost insertion, then we need to insert that customer in that position. So that's the greedy approach proposed as the repair operator here. take a look in the illustration. I just prepare one customer for the example. Let's say you have a route, and then the part of the route is C1, C2, and C3. And then you have two positions for the insertion. You have P1 and then you have P2. And then now you need to consider where should the greedy heuristic insert the C4? Is it in the P1 or is it in the P2? Then I have provided the information here, the delta F C4 P1. It means that the cost to insert C4 in the position P1 equals to 20, while the delta F C4 P2 equals to 15. Then it should be a very short answer. Which position should you choose based on the definition of greedy heuristic? Yep, thank you, Dr. Arfin. This should be P2. Okay, so that's the answer for this illustration. And I hope that after we understand the definition of the CVRP, we want to minimize the total traveling cost. I really want to I want to ask another question: how to calculate the delta FIP in CVRP? Let's say how to calculate the delta FC4P2. Could someone type the formulation? The CVRP, as we discussed earlier, we want to minimize the total traveling distance, right? Then how to calculate the delta FIP? Let's say I want you to calculate the delta FC4P2. Please, could you provide me the formulation? Sorry, I will drink. Okay. C12 plus C24 minus C14. A little bit. It seems like that, but the index is wrong. Yeah. Okay. Want to make another try? Okay. Okay, C4. Oh, I would like to calculate this one, Dr. Arfin, the delta. Yeah, not this one. Yeah, I think you are looking at this one, right? So I would like to know how to calculate the delta FC for P2. Okay. Okay. Okay, I see 2, 3, C24. Oh, okay. It should be this one. C24 plus C43, and then minus C23. Okay. Remember, you need to calculate the increment. Yeah, the increment of the cost. That is the insertion cost. Thank you for the answer. Oh, thank you. Also, this is the full calculation. C12, C24. Yeah, actually, that is the full calculation, but in the code, try to shorten the calculation. That will be useful for the computational time. You do not need to calculate the full distance of the path you just need to calculate the increment cost or the insertion cost, which only happens in this area or in this region. But that's correct. That is the full calculation. Thank you, Miss Mr. or Mrs. Uyendang. Okay, so let's move on with the you're welcome. Then let's move to the regret to heuristic. And I put Demir et al. In 2012, pardon me, because when I designed the PPT and I designed the code, the regret to heuristic in my mind is the version of Professor Emrah Demir. And after I coded, after I designed the PPT, then I just try to reread the regret to heuristic proposed by Professor Rotti and Kissinger. It's a little bit different. Okay, so that's why I need to write the version here. It is the regret to heuristic that I shared with you is the version of Professor Demir in 2012. Okay, so but the main purpose of the regret to heuristic is the same. So the class of regret heuristics was proposed to overcome the main weakness of greedy heuristic, that is the myopic behavior. Okay, so let's take a look on the what is myopic behavior. Start with the greedy again. Okay, the greedy approach, and I believe you have already got used to see this example: C1, C2, C3, P1, and P2. Then, okay, sorry. Let's say when we want to insert C4 in the P2, it is 15. And then when we want to insert C4 in P1, it is 20. Now we have C5, okay? C5, when we want to insert it into P2, it is 18. And then when we want to insert C5 in the P1, it is 40. Okay, now you have these 4 types of information. Then based on the greedy approach, which customer and which position will be selected to be inserted? You have C4 and C5, and then you have each of the customer have 2 possible positions. Then please determine which customer and which position. C4 and P2. Yes, thank you, Dr. Wira. Yeah, that is the C4 and P2. For the greedy approach, we will insert the C4 at P2. And then now we have C1, C2, C4, and C3. Then we have P1, P2, and P3. Okay, we have 3 possible positions now. And the left customer to be inserted is C5. Okay, C5 is inserted. Let's consider this situation. Okay, this is an illustration why the regret to heuristic is proposed. C5, when we try to insert C5 in P1, it results in 40. And then when we try to insert in P2, it results in 48, larger than the 40. And then when we try to insert in P3, it is also still larger than 40. So it means that based on the greedy approach, we will select the this value or this insertion. That is, we want to insert the C5 into the P1. Okay. Then it means that the total cost that we obtain is TC, the total cost in the previous solution, plus 15 plus 40, right? That is the total cost when we use the greedy approach. Now, by considering the same thing, but we want to use the regret heuristic, okay, the idea of the regret heuristic, we need to calculate the difference, okay, between the first best cost and the second best cost. So for the first best cost, it's 15, and then this is the second best cost is 20. So 20 minus 15 is 5. Oh, sorry, I will use pointer. Okay, so let's consider the C4 here. Then 20 minus 15 is 5 here. And then we consider the C5. 40 minus 18 is 22. So now we want to select the customer not only with the least cost, but also the largest value of this. Okay, so between 5 and 22, of course, based on the largest value, we need to select the C5. Then after selecting C5, we need to insert the customer in the least cost position. That means we will select C5 and then we will insert it in P2. Okay, that is the first position, the first choice. We select C5 and we insert it in P2. Then it will become C1, C2, and C5 and C3. Then we try to insert to consider the insertion of C4 in P1, P2, and P3. Then these are the cost. Okay, these are the cost 20, 25, and 21. Then for sure we will select the least cost 20 here, and that means what we have here is TC plus 18 plus 20. If you still remember that in the first one, if we use the greedy approach, we get TC plus 15 plus 40, right? But if we use the concept of the regret heuristic, we get TC plus 18 plus 20, which means in the end of the solution, we get lower cost compared to the greedy approach. So this is the regret heuristic. Okay. Now we will generalize the previous observation, the observation that we have just discussed now. We have the, I hope that you still remember this guy, the delta FIP. Then we will turn it into delta FIQ. Okay. So the delta FIP, as you guys still remember, is the cost change or the objective change if we insert the customer I into the position P. Now we change it into delta FIQ. Delta FIQ is the change in the objective value incurred by inserting customer I into its Q cheapest position. Okay, into its Q cheapest position. So then the customer that will be inserted into the solution, we need to select a customer. Okay, in the list of the customers the removed customers, just like in the previous example, we have C4 and C5. Then we need to determine the maximum, this one, argmax delta FI2 minus delta FI1. Okay, the second best insertion minus the first best insertion. Then we take the customer that results in the highest value of this calculation. Then this calculation itself is often known as regret cost. Okay, in this term, we call it regret cost. I'm not sure in other areas how do they call them, but in here we call it as regret cost. Okay, then that is for the regret 2 heuristic. That's okay, a short story why we call it 2, because we only consider the second best cost. So we have in the paper, you may find not only regret 2, but you can also find most of them regret 3. So regret 3 means you consider not only the second best cost, but you also consider the third best cost. And the generalized regret heuristic is regret K. Okay, A, B, C, D, F, G, K. Regret K heuristic means that you need to calculate the first, the second, the third, until the last best insertion. Then you take the summation. You will use those information to calculate the regret cost. Okay, so that's why here I only present the most simple one, the simplest regret heuristic, that is the regret 2 heuristic. Now, after considering the greedy, the regret heuristic, now we move a little bit further to the modified repair heuristics. Okay, still on the greedy and regret 2 heuristics, but we need to modify something in the mechanism. Here, all the aforementioned repair operators, of course they aim to find the best insertion position, but most of them, since they will result in the locally best insertion position. Then Professor Ropke and Kissinger in 2016, in 2006, they proposed a modification by including the noise. Okay, we will see what is noise. Okay, by including the noise into the calculated objective function. And maybe you will think that does that make sense to include the noise? But by the experimental results of Professor Ropke and Kissinger's, they confirm the benefit that including the noise, okay, into the calculate objective function for these repair heuristics, they can obtain better quality solutions. And these are best solely based on experimental results. There are no theorems or proofs that says that it is correct for all variants of the problems, but you may confirm it by the experimental results. Now, I will give an example of the greedy insertion. Come back with this example, okay? Don't get bored with this one. So we have the delta FCP P1 equals to 20, and then we have delta FC4 P2 equals to 15, okay? Then by considering only the greedy insertion, we will choose this one, right? We will insert the C4 in P2. But now, considering the noise means that we will adjust the objective value or the cost obtained original. We will adjust the original cost. Here I used my own concept, okay, just to make it simple. I just multiply the 20 here with the random between 0 and 1, okay? I clarify that this is not the way Professor Ropke and Kissinger used, but I use this illustration just to create a simple understanding of how we add the noise, okay? So we modify the noise by multiplying the original cost with some noise that here, for example, the random value between 0 and 1. And then let's say 20, and then you got 0.5 resulted from the random generator. Then 20 multiplied by 0.5, it equals to 10. Then the next one, you calculate the second position, and then you multiply it with another random value, and then the random generator give you 0.8, and then it's 12. So based on this modified greedy insertion, you will not choose this one anymore. You will choose instead, you will choose the position one, okay? And then that's the answer. You will insert the C4, not in P2, but you will insert the C4 in P1. That's the result of considering the noise in the objective value. Now, come back to the exercise again. Let's see, you are given with this information, okay? Which customer and position will be selected if, let's consider the first question, okay, before moving into the second one. So just try to answer the first question first. Regret to insertion is applied. So try to answer this one. Regret to insertion is applied. Okay. You may write down the your calculations or your answer in the chat. And if you want to ask something related to this information, this exercise, please just turn on your mic, okay? C5 P1. Yep, that's correct for the first question. Dr. Artfin. So I will explain it a bit further because I put some new information, some aspects here, some new aspects here. If you take you calculate the regret cost, 26 minus 7, sorry, it's not the C5. Then you first we could check the regret cost. 26 minus 17, it should be 9, right? 9, and then the regret cost of C5 is 28 minus 19 is also 9. Okay, both is 9. So which one should we choose? According to Professor Rocky and Bissinger, follow the greedy approach. So if you got this situation, okay, then just choose the least cost, the customer that results in the least cost insertion, which means we need to insert the C4 in P1. Yeah, so that's the answer for number 1. Then we move to number 2.
Pancha?
Oh, yes, Dr. Arfin.
I thought it was always P1 minus P2. So that's why.
No, it's not always P1 minus P2, but the second best cost minus the first best cost.
Oh, okay.
Yeah. Okay, so it should be the second best cost minus the first best cost, regardless the position. Okay. Okay, then yeah, it's quite tricky for question number 1. Let's move to the question number 2. Regret insertion with noise is applied. So I have provided the random value generated for each original cost. It's totally different, right? 0.8, 0.3, 0.7, and 0.6. Okay, I actually have not calculated it yet. So let's see, 0.8 times 17, it's 13.6. Then 0.3 times 26 is 7.8. Then you take the negative, then minus 13.6. So it's 5.8. This is C4. Then for C5, wait a moment, I will try to calculate the result. 13.3 and 28 times 0.6, 16.8. 3.5. This is C5. Okay. Yes, Dr. Artfin, you are correct that it should be C4 in P2. I will write down that. This should be P1. It should be P2. And this is P2. Okay. Correct me if I'm wrong. And that is the answer I have put in the chat. So since we calculate the regret cost of C4 and C5, and the largest one is the C4, then we need to determine in which position we need to insert the C4, and it should be the position that results in the least cost. Then it should be the P2. Okay. Although the original one is 26, but after we multiply it with the random value 0.3, it results in 7.8. Then that means we need to insert the C4 in P2 instead of P1. Okay, so that's the exercise for the repair operators. Now we move, after we have discussed the destroy and repair operators. I hope that all the participants still remember what comes after the destroy and repair operators. It should be the how to accept the new solution. Okay, so after you apply the destroy operators, you remove a subset of customers. Then you try to insert it back by using a repair operator. Then you create a whole new solution, right? That solution, will we accept it or not? That's what we will talk here in the acceptance criteria. Professor Rapi and Kissinger in 2006, they adopt the simulated annealing framework. Okay, I hope maybe you guys have ever heard about simulated annealing framework. So this framework will help to get out from the trap of the local optima. What is the rule? So I write down here. So please remember, you still remember the three types of S, right? The S accent, the S, and S star. Okay, so the new solution is represented by the S star. Oh, sorry, the S accent, and then the current solution, the old one. Okay, the old one is represented by the original S, and the S star means the best solution so far. If the objective value of the new solution is less than the objective value of the current solution, then we will just directly accept it. Okay, simply we just replace the current or the old solution with the new solution. Then we will further check if the current solution if the new solution, okay, less than the best known solution so far, then we need to replace the best known solution so far with the new one. Okay, so this is what the best scenario that we expect from the meta heuristic. We always get the best known solution. Okay, however, how that we need to consider the second scenario in which the new solution is not better than the old solution. Okay, it should be in the else part. Okay, this one. So if the new solution generated by the destroy and repair operator is not better than the old solution, we can still accept the new solution. Accept means to replace the old solution with the new generated solution. Okay, but we need to consider these criteria. Okay, first you need to generate the random value. This is totally handled by the random generator, random from 0 and 1. And if we need to calculate another value, is the epsilon powered by minus objective value of the new solution minus the objective value of the old solution divided by T. And the T here is the current temperature. Okay. This is merely a calculation, so you could use calculator later. I will provide you an exercise to calculate it. Then if the generated random value is less than the calculated value here on the right hand side, then we will still accept the newly generated solution as to replace the old solution, although the new generated solution has worse objective value. Okay, so that's the main point of the simulated annealing. It will not directly reject the worst solution, but it will still consider the worst solution by this criteria. Okay, then now another exercise, short exercise, is kind of calculation. If the objective of the old solution is 750 and the objective value of the new solution is 755, which means is worse in the CVRP because we want to minimize the total traveling distance. Then the T here, or the current temperature, is 30. And then when we generate the random number is 0.3, then the newly generated solution replaces the old solution. Is that correct or not? You can use calculator or true or false? divided by 30. 0.6. Give you the hint. You see the epsilon minus 755 minus 7 divided by 30. It is 0.6. Right. Please correct me if I'm wrong. When I calculate the right hand side, it should be that one, I think. It's like 0.6065 and so on. So I just take the first decimal. Okay, so thank you, Mrs. Tina. The question is correct that the newly generated solution replaces the old solution, because when we compare 0.3 with 0.6, then 0.3 is less, for sure is less than 0.6, then it replaces the newly generated solution replaces the old solution. Okay, then. Okay, now I will not talk much about how to tune the parameter, so I will just give a glimpse of information about the T, okay, or the temperature. First, we don't know, right? We suddenly talk about T, but where does the T come from? The T starts with an initial temperature T0, okay? In the pseudocode or in the framework that I have posted earlier in the earlier slide, that the T starts with T0. In every iteration, the value of T reduce, okay? It doesn't increase, it reduce by the following formulation. T equals to T times alpha, where alpha is the cooling rate and the value of alpha, again, it is controlled, it is the parameter, part of the parameter ALNS parameters. So it will be determined in the parameter tuning. And then Professor Hockey and Pissingers in 2006, they proposed a problem-dependent parameter. What I could say up to now is just this one, a problem-dependent parameter for calculating the T start. Okay, so sorry, the T0. Okay, the T0. It's not T start. Okay, pay attention. T0. So it means that for every problem, let's say you have 10 different problems to solve, then each problem will have different value of T0. Okay, it depends on the problem, but I will not explain too far about this one. What I want to give some sense, I want to give you some sense about the impact of the T. Then let's try with this let's see with this statement. When the T reduces, the change to accept worse solutions gets higher. Is it true or false? Hint, okay, I provide you the hint. Compare the following two cases. The main difference is between these two cases, only the T. This is the T equals to 30. This one, the T equals to 10. It means that the second one is the case when the T has reduced, right? And then you may compare these two cases to clarify whether this statement is correct or not. Okay. remember that the I will provide you with this calculation equals to okay. So I have provided the calculation of the right hand side. Then try to recall and what is the answer for the statement. Okay, seems like no one answer this. Okay, so after Dr. Wira put the result or the decision of the case, which means the first case it is true and the second case it is false, then it means that when the temperature or the T reduces, it is correct that it is false that the change to accept the worst solution gets higher. Okay, so what is correct is the change to accept the worst solution also reduces. Okay, so when the T reduces, the change to accept the worst solution reduces. Okay, let's go to the okay, after talking about the acceptance criteria, then we talk about one of the another specialty in the adaptive large neighborhood search, that is the adaptive weight adjustments. So as I explained earlier, that the probability of selecting operators, it really looks like a roulette wheel. So, but the difference is we need to adjust the probability of selecting operators periodically. Okay. Now I recall the remaining symbols. Okay, I recall the remaining symbols. We have 5 new symbols here. We have eta s, it's to the updating period of weights, and then we have wi minus, wi positive, p minus, and p positive. Each of them represents the weight associated with the destroy operator, repair operator, and then p represents the probabilities of the destroy operators to be selected, and the p plus represent the probabilities of repair operator to be selected. Now, consider that the eta s, or the updating period of weights, equals to 100. Okay, so it means that you will update the probability of those operators every 100 iterations. Okay, then you have wij minus, you have wij plus. Okay, it is an extension of the it is the extension of the wi minus here and the wi plus. So wij minus is the wi minus for segment j. Okay, and for example, segment j means the first, let's say the first segment is the first 100 iterations. Okay, so that's the meaning of segment j. Then how to calculate the weight? Okay, take a look on this formulation. Okay, wij plus 1 equals to wij 1 minus r plus r times the phi divided by theta I. The formulation is quite long, but I will try to explain it. So the wi J plus 1, it means that the weight of the next segment, okay, J plus 1 of the next segment, it depends on two things, okay? It depends on two things, the Wij, or the weight, the current weight of the operator, okay? The current weight of the operator, Wij, plus the pi I divided by theta I. What is the pi I? Pi I is the total score of operator I obtained during the last segment. It means that in 100 iterations, for example, okay, in 100 iterations, we need to keep track the total score of each operator. Okay, so you will got the total score of each operator within the 100 iterations. That's the phi, the pi I. And then theta I is the number of times we have attempted to use the operator I during the last segment. So within the 100, let's say, again, with this example, 100, for sure, we will not use the same, the change to use the same operator again and again until 100 times is very low, okay? It means that we need to track how many times we use operator A, B, C, and so on. That is the theta I, okay? Together with the R, P, pi I, theta I, we can calculate the weight associated to the destroy operator or to repair operator in the next segment, the J plus 1. Okay, the reaction of the R, or the reaction factor itself, it is also another parameter of ALNS. Okay, then you up to now, then you will think, oh my God, there are a lot of parameters in ALNS. Yes, that is one. I could say that one of the weakness of ALNS is there are a lot of parameters to control. Yeah. Then you have how to calculate the probability. Okay, so the end or the output of the adaptive weight adjustment is the probability of the destroy operator, the probability of the repair operator, the new probabilities. Then the new probabilities is calculated based on the weight. Okay, so there are two steps here. First, you need to calculate the weight, which is expressed by this formulation. Then you need to calculate the P, or the probability. Okay, it's simply like the formulation expressed here. If you want to calculate the it should be PI here, not PJ. Okay. Later I will correct it. It should be PI, or the probability of selecting operator I, destroy operator I, equals to the weight associated with the operator I divided by the total weight. That's all. Okay. So the weight of the operator I divided by the total weight. That's how we calculate the probability of operator I. Okay. Then else. Oh, how to calculate the pi I? Okay, because here the theta I is straightforward because you just need to keep track the number of times you use the operator. Okay, but it's for the pi I is the score, and how do we give the score to the operator? Then this is proposed by Professor Ropke and Bissinger in 2006, another 3 parameter to consider. Okay, we have sigma 1, sigma 2, and sigma 3. But we can simply understand this easily. Sigma 1 it means that you will give the score as much as sigma 1 if the new global best solution is resulted. Okay, so if the the destroy and the repair operator finds the new global best solution, then you will add the score sigma 1 to the associated destroy and repair operators. For sigma 2, then you can see the second sentence: the cost of the new solution produced by the destroy and repair operator is better than the cost of current solution. But given there is an additional condition, The resulted, okay, the resulted remove and insert operation means that the newly generated solution has not been accepted before. Okay, has not been accepted before. This is the original idea of Professor Ropke and Pissinger. But some of researchers, including me, we try to make it simple, more simpler. So we just ignore the first sentence here. We do not keep track the solution that has been accepted before. So simply we just consider that if the cost of the new solution is better than the cost of the current solution, then we will add sigma 2, the score sigma 2 to the associated removal and destroy operator. Okay. And then the third one, similarly, okay, it's similar to the second case, but this case is when the cost of the new solution is worse than the cost of the current solution, but the solution was accepted by the simulated annealing framework. As we remember that when we apply the simulated annealing, we will not directly reject the worst solution. We can still accept the worst solution by using a criteria that we have discussed earlier. Then if we accept that worst solution and the solution has not been accepted before, okay, then the professors Ropke and Pissinger proposed sigma 3 to be added to the associated destroy and repair operator. Okay, so we only consider these three cases. What happened with the other cases? 0 score. Okay, so there are no scores if the other cases happen with the destroy and the repair operators. Now, another exercise, please. Hello, everyone. I hope that you guys still awake. Okay, it's just a calculation now. Based on these parameters, okay, and the description that I have already explained, let the sigma 1 equals to 33, sigma 2 equals to 9, sigma 3 equals to 13, okay? These are given. In ALNS iteration, the total scores so far for the destroy and repair operators are as follow. Random removal 400, shell removal 300, burst removal 250, and the greedy insertion is 450, regret to insertion is 500. Then the shell removal and greedy insertion are selected, and they together produce a solution that has been accepted before, and the cost of the new solution is better than the cost of current solution. What are the current scores after considering this case of the shell removal and greedy insertion? Okay, so please pay attention to this statement, okay? They together produce a solution that has been accepted before, and the cost of the new solution is better than the cost of the current solution. So what are the current scores of the shell removal and greedy insertion? Take a look. This is the shell removal score, and this is the greedy insertion score. Okay. Greedy is 450. Oh, just the scores, Dr. Wira. Like we do not calculate the probability. Yeah, we just calculate the scores, the current scores. Okay. So how about the others? Where are the others? So the shell removal, let's say the shell removal is 300, right? Then and the greedy insertion it's 450. Then that is this is the condition before we consider this. And after we consider this statement, the current score, shell removal and greedy insertion. be something like this. Don't worry, just keep trying. Keep trying, everyone. Okay, seems like no one trying to to answer this. Okay, so okay, so this one since they have produced a solution that has been accepted before, and we based on the table in the Professor Robke and Pissinger. If it has been accepted before, then we cannot include any score into the shell removal score into the scores. So it means that actually the shell removal and the greedy insertion, they still have the same scores based on the score adjustment parameters proposed by Professor Robke and Pissinger. Okay, so the main part is it has been accepted before, but in several papers, don't be surprised, including one of my papers, I do not consider this one. So as long as the solution is better than the cost of the current solution, then I will apply the it should be the sigma 2, because the new solution is better than the cost of the current solution. Yeah. So that's the answer. Okay, based on this table, the answer, the scores, the current scores are still the same. Okay, plus 9. Yeah, plus 9. Yeah, that's right, Dr. Rira. So if we do not consider this one, we need to plus 9. Okay, then what's next? What is this? Okay. I hope that everyone can still join, okay? So first, if you include 3 removal operators and 2 removal operators, this one is complex. Okay, so everyone, you could give me the sign. Are you still here? Okay, you can put hands or put any kind of emoticon on your screen to let me know whether you are still here. Then now let's consider the first. Okay, thank you. So the first question is, if you include 3 removal operators and 2 repair operators, the total scores of the 3 removal operators, okay, consider the total scores of 3 removal operators are less than, equal to, or greater than the total scores of the 2 repair operators. Okay, just keep trying, everyone. Less than, equal to, or greater than. Okay. Other participants? Other participants, I hope that especially the students, or do you get lost, everyone? Please just ask me anything about the ALNS in the middle if you want. Okay, seems like no one will try to answer. Okay, so actually, okay, so here the information is 3 removal operators and 2 repair operators. Then Dr. Arvin has been leaving. Oh, maybe Dr. Arvin and Dr. Yogi travel to other places. Okay, so it should be less than, equal, or greater than. The answer is equal to. Okay, so it should be equal to, because when we select a destroy operator, we also select a repair operator. Then it means that we will always give the same score to one destroy operator and to one repair operator. So and here what I ask is the total scores. So the scores will not go anywhere. They will just go to a specific removal operator or a specific repair operator, but the total scores, they are still the same. Okay. Then maybe I will try to answer this one because it's quiet. Please refer to the following formula. Okay, the following formula, if you still remember, it's the how to calculate the weight, okay, or to adjust the weight in the section J+1. Okay, briefly explain the meaning of R in the above formulation. What I would like to explain here is the impact of R. Okay, the impact of R here, we could see that it's like a weight. The R represents the weight for the Wij and for the pi I divided by the theta I. So, and we take a look that the left hand side is 1 minus R and the right hand side it's only R, which means that if we try to enlarge the R, it means that we only pay attention to the last segment, okay? Because the pi I and the theta I, we collect it during only the last segment, okay? After we collect the total scores and the total number of times, let's say within 100 iterations, then the next 100 iterations is totally not connected with the previous 100 iterations. So we will start to calculate the score and the number of times from 0. That's the how to calculate the pi I and theta I. Then it means that if we enlarge the R, which means let's say 0.9, and this part it will automatically be 1 minus 0.9 is 0.1. So we put more emphasis on the present states of the ALNS compared to the historical records. However, if we make the R greater, then we put more emphasis on the historical records, because the Wij, it's resulted from the Wij minus 1. The Wij minus 1 is resulted by the Wij minus 2. So it is connected with the previous historical records. And if we put more higher value in R, it means that we want the historical records has a higher influence to the Wij plus 1. Okay, so that's the how to interpret the R, the reaction factor. Demo. Okay, so finally comes to the demo. Okay, let's see. Could everyone see my screen? I put the kind of the Visual Studio. Okay, thank you, Dr. Rita. So I will not explain the code, don't worry. So what I would like to share is we have learned the components of each ALNS, like the destroy and repair, and then the acceptance criteria, the weight adjustment. Then we would like to see how it works holistically, okay? Of course, here I will just explain it briefly. We start with probability. I hope that this font size is large enough. Could the participants read the sentence here? Okay, thank you. So the initial probability of removal operators and the initial probability of repair operators, as I have told in the earlier slide, it should be equally likely, okay? So this is the first one, 0.2, and this is the cumulative, okay? 0.2, and then the second one is 0.4 is the cumulative probability, which means that the probability of selecting the operator 2 is only 0.4 minus 0.2 is also 0.2, 0.6, 0.8, and 1, which means that they are divided equally likely. And here we have 4 repair operators. Okay, I include 4 repair operators here, and they are also divided equally likely. 0.25, 0.25, 0.25, and 0.25. Okay. Then, okay, here is the initial solution, the route visualization. Okay, could I ask if the participants still remember the solution representation in the earlier slide, how many vehicles here? Okay, 6 vehicles. Okay, 6 vehicles here. And yeah, I have put here the total vehicle 6. The total objective is 1066. And then as I remember, in the instance or in the problem, the maximum capacity of each delivery van or the vehicle is 100, and we can see that 4 of the vehicles, they are fully loaded, while the 2 other vehicles, they are not full truckloads. Okay, and here is the total distance traveled by each vehicle, and if you take the summation of all of them, it will result in 1066. Okay, then after we generate the initial solution, here is the T0. Does anyone still remember what is the function of temperature in which part? Destroy repair operator, acceptance criteria, or the adaptive weight adjustment? What is the function of the T0 and the T? It is in the, yep, thank you, Mrs. Tina. That's right. It's in the acceptance. Okay, it's in the acceptance. So this is the initial temperature, as I have explained before, the T0. And then initially in the ALNS, we will set the T, only the T. Okay, we have T0 and T. The T is the current temperature, and the current temperature equals to T0 in the beginning. Okay, so take a look here. This is 1076.54, and this is also 1076.54. Then the first iteration, okay, in the code, in the C++, especially, we will start everything with 0, okay, not 1. We will start everything with 0. So iteration 0, this is the current solution, which means the same with the initial solution. The total objective is 1066. We have 6 vehicles used here. Then the first thing before we apply the destroy and removal operators, we need to determine the number of customers to be removed. Okay, then in the code here, they generate 8. Okay, so we need to remove 8 customers. Then let's take a look. This is the selection probability. Remember, it's like a roulette wheel. Then you need to select the generate a random value, and the random value is 0.563585. Then in this area, or in this region, the worst removal probabilistic is applied. And when the removal phase, or when we have already applied the worst removal probabilistic operator, this is the removed nodes: 29, 14, 16, 12, 2, 32, 17, 7. Okay, and after removing these 8 nodes, then this is the visualization of the routes. Of course, they become shorter because we have removed 8 nodes. And then the total objective, it reduced a lot because we have removed 8 nodes again. From 1066, it becomes 880. Okay. Then what is the next phase after the destroy operator? What is the next phase after we destroy or remove the customers? What should we do after this? Yeah. Thank you, Dr. Wira and Mrs. Tina. That's right. After we destroy the solution, we repair. Okay, we select one repair operator, and then here, let me see. Okay, take a look on this part. The regret to insertion is applied. Okay, then after it the regret to insertion has finished, it means that we have successfully inserted all the removed customers, the 8 customers removed earlier, into the routes. And here the total objective is 1013. Okay, if all the participants still remember, the initial solution is 1066. Okay, and then when you repair it, the total objective becomes 1013. So in this case, will we accept the newly generated solution? The old solution is 1066 and the new solution is 1013. Will we accept the new solution and replace the old solution with the new generated solution? Yeah. Yes. Okay. So thank you, Dr. Wira. Thank you, Mr. Algreg. So that's right, because it's certainly better, right? It's better than the old solution, so we replace it. Okay, which means the best solution found. Okay, best solution found 1013, because this is just the first iteration, right? So it means that the best known solution equals to the initial solution. Okay, so the best known solution found 1013, and it returns to the first again, it will continue to the next iteration. Okay, and it will keeps going until the termination criteria is achieved. Okay, when does it stop? I simply set it here equals to the maximum iterations. Okay, so after it reached the maximum iteration, let's say 25,000, then it will stop and give you the best known solution. Okay, now my question is, my question is that after we have performed one complete iteration, then do we update the scores? And this is the first question. Do we update the scores? The second question is, do we update the probabilities of selecting the operators? Okay, there are 2 questions. The first one, do we update the scores of the operators? The second one, do we update the probability of the operators? I will show you the, okay. This is the eta S, okay? The updating period of probability. Okay, so updating the score, yes. Updating the probability, no. That's correct. Thank you, Dr. Wira. So here it means that we update the score, of course, but we do not update the probability. Then I will just show the, when we run it. Oh, wait a moment. Okay, so when you successfully design the ALNS, it should improve your initial solution, right? Let's see this one. This is the initial solution, 1066, and then the ALNS have run for 25,000, as I remember. Yep, 25,000, and then from 1,066, then it can reduce to 771, and this is the route, the total routes. It still have 6 vehicles with totally different routes, the sequence of customers, and take a look on the capacity of the vehicles, that it doesn't exceed the 100, the value of 100. It means that the solution here is feasible in terms of the capacity. Okay, so this is the demo of the ALNS. And okay, Dr. Mira, how many is there? I still have
I think we can
still
have 30 more minutes to discuss
okay.
the rest of your your sharing session.
Okay, thank you, Dr. Mira. So this is the final session of the our webinar tonight. It's just the tips and trick for developing state-of-the-art ALNS. I will briefly discuss how it's based on my perspective. How do the researchers in the world try to develop, to push the boundaries of ALNS? So the first one is the most common one, is to propose a set of new destroy and repair operators. I take the paper from Kaskin and Katai in 2016. They are dealing with electric vehicle routing problem with time windows and partial recharge. The main difference here, if you consider the CVRP and the electric vehicles, of course, for the electric vehicles, you may take a look that they consider the state of the battery for each vehicle, right? For each vehicle means that if they have low level of the battery, they need to visit the recharging station to recharge their battery before going to other customers. It means that a new decision compared to the CVRP exists. In the CVRP, you do not need to decide when the vehicles need to refuel, but here in the electric vehicles, you need to consider when you need to recharge the vehicle and how much battery level you want to recharge. Okay, since the new decisions exist or appear in this problem, okay, in this problem, it means that it's worth to propose new operators for dealing with the placement of recharging stations. Okay, so when you you are doing your research later and you plan to apply, plan to develop the ALNS, and your problem is new, then it means that there is a possibility for you to develop a new destroy and a new repair operator based on the characteristics of the problem. That is the first one. And then the second one is is a more technical aspect here. I will just briefly discuss about this. We propose an acceleration technique to deal with the feasibility of the solution. The more constraints the problem has, the higher the complexity level is. It means that maybe the complexity of the feasibility checking function, it will grow in terms of the complexity. But I provide, there are 3 papers, including in our papers. We propose acceleration techniques, and I will just briefly discuss the basic concept of the acceleration technique here. Suppose that we are dealing not with the CVRP, but we add time windows. Okay, so take a look that C1 here, they have an additional information that states the C1 can be visited in between E1 and L1. So outside this range, the C1 is unavailable to be visited. Okay, and for each customer, each of them has different values of E and L. And it turns the problem into the vehicle routing problem with time windows. Then let's say you have C5 that you want to insert, okay? You want to try to insert it in between the depot and C1. You try to insert it here, you try to insert here, 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 and here. It means that you have 5 possible positions. Then the question is, how do we check whether the insertion of C5 is feasible or not? Then we might think a formula like Mr. or Mrs. Uyendang has ever mentioned earlier. We will check completely from, let's say, C5, then we will put C5 here. Then we'll check, okay, that from the source of the good, we visit C5, C1, C2, C3, C4, and come back to the depot. Does it still produce a feasible solution? The classical way is the one that I mentioned, to check the whole route. That means we need to check the whole route 5 times because we try to insert it in 5 different positions. Then how if we deal with 50 customers, 100 customers, and so on? It means it will take more and more time to check the feasibility of the insertion. Then the solution proposed in these papers, they try to accelerate the insertion by developing a formula that cut down the computational time for the feasibility solution. Okay, isn't it more beautiful that if we can calculate whether there is a violation or not by only using one formula? That's what researchers try to do nowadays. One of them, they try to create only one expression or just maybe a few expressions. And here in Snyder et al. In 2013, although it is not implemented in the ALNS, but this is like a showcase, I would like to say. Like, let's say you have the route 0 to this one is like you visit a subset of customers, and then X is the customer, and then V, Y, another customer, and then in the end you visit the depot. It is generated by 2 paths, from 0 to X and from Y to 0 by inserting the customer fee in between, right? In between. So what the classical way to check the time windows violation is that you try to calculate it in every node until the end of the route. But Snyder et al. In 2013, the feasibility of R can be checked by only using one formula, that is this one. I will not discuss further about this, okay? But what I would like to emphasize is proposing an acceleration technique is one of what the researchers in the world are doing to push the boundaries of the state of the art. Then the next one is to hybridize other heuristics or methods into the framework of ALNS. The one, I could say that one of the well-known framework is local search, and I would like to briefly describe what is local search. Okay, here it is a very simple route. It starts with 1 to 2 to 3 to 4. Okay, and goes back to 1. And then if we take a look on the visualization, somehow it looks inefficient because it visits 3. I mean, there is let me use the pointer. This part, it looks not efficient. And then if we try to improve it, maybe it will become a shorter route. And if we take a look on the solution representation, 1 2 3 4 1, it becomes 1 2 4 3 1. Okay, from the solution representation, what we need to do is only to swap the position of 3 and 4. First the sequence is 3 to 4, and now the sequence is 4 to 3. Okay, that is the concept. It can improve, the local search can improve further the results of the ALNS, but actually how do we know that we need to swap 3 and 4, right? How do we know that? It means we need to try all the combinations from 2 to 3. You swap it, does it result better? 2 to 4, 3 to 4. And that becomes a simple way of the local search mechanism for swapping operation. Okay. So that is the main one, the simple idea of the local search. And then another one is to integrate the mathematical model. Okay, for example, set partitioning problem, set covering problem, set packing problem, etc. And I will not discuss about this mathematical model for sure, but this is, I would like to say that a lot of researchers now to try to use the set partitioning problem, which actually has been proposed, like you can see 1969 is like 60 years ago, and it's still be used until now. So we cannot underestimate the research of in the past, because we are still using it up to date. And okay, how to implement it? I will briefly discuss the set, how to implement the set partitioning problem. Let's say you now, when you apply the ALNS, you destroy and repair, then you produce new solutions, but you do not keep track on the routes. You just compare your old solution and the new solutions. And then maybe you will replace the the old solution with the new solution. Okay. But what you're working is, what you are working at is just the old solution, new solution. That's all. Okay. But in the we can make use the historical records of the routes, like when you generate the routes in the first iteration, second iteration, third iteration, and so on, you collect all those routes. Okay, you collect all those routes, and it is represented by these columns, or these rows. I mean, these rows. Okay, this is like the first route, the first collected route, the second collected route, and so on. You collect all the routes. Okay, you collect all the historical records of the solutions. Then, based on the pool, okay, the collection of these routes, you will, of course, you will optimize, or you will combine all those routes to create one full solution. And it may, what is the benefit? It may result in a better solution. And it has been proved by several research. But if you consider this technique, you can improve the quality of the solution. Okay. So again, it's based on the experimental result. There are no proofs. Okay. Is there, just like in the mathematics, we prove everything, but here we just prove whether the techniques are effective or not by using experimental results. Okay, so I think that's all my presentation tonight. Thank you for listening me for around like 2 hours and a half, I believe. Thank you so much. So these are the references. Okay. If you are interested, please let me know. I think I will send the PPT to Dr. Wira in case someone needs this.
Yeah, actually, a lot of people already asking me, can I see the record? Can I get the PPT? So by the permission of Dr. Panca, I think I will share it to you later. Just maybe like give me some time to like upload it to the YouTube so that you can have more convenience of frameworks to see this recording again, because sometimes if we just give the download links from the Zoom, it will be too big. But if you put it in YouTube, perhaps you can like have more speed. Somehow the platform is better for rewatch the webinar and things like this. Well, anyway, Dr. Panca, you have a very wonderful explanation of such a complex frameworks. We really enjoyed it. Thank you very much. But let me ask everyone, if you have any questions, perhaps it's a good time before we end the session. No, not yet. Okay, maybe if not, maybe just one question, Dr. Panca. Like I mentioned earlier, so many people ask me, like, yeah, we know that it surely needs some programming skills to implement these type of algorithms, but maybe you have, can you share some experience on we know that we should digest it this by implementing it in a programming language, but what is the most convenient way to go through it? Perhaps if you have some experience on it, so that we can share this to everyone that interested on learning these algorithms and meta-heuristic stuff.
Wow. Thank you, Dr. Wira. Thank you, Dr. Wira, for the question.
Yeah.
Okay. I think for me, only based on my experience. Of course, the first one we need to learn how to code, but maybe we can decide which programming language do we want to learn first.
Okay.
And do not try to learn all the language at the same time. Like me at that time, because our lab we are using C++ only. So yeah, I start learning it from C++.
Okay.
Then I focus for some weeks to learn the basic of the C++. I do not try to cover everything in the C++ because I know there are too many things in the C++. So what I learned is actually the code of Dr. Wira. If you still remember, you have written the code of simulated annealing that time. Yeah, and it really gives me the insight what parts of C++ that I need to learn. So yeah, I do not need to learn all. I just need to learn the important parts that we need to use in the meta-heuristics. That's the first thing. Do not need to learn all. Just take some important things of the programming language for the meta-heuristics. And the next one, I think we need supports.
Okay.
We need supports from our friends, because at that time I learned the meta-heuristic most often myself. But when I got bugs, of course, when we code the first time, we got a lot of bugs, the unknown bugs. And then I think the best way is to ask friends, to discuss with friends who also work in the same area. Yeah, that's how I tried to improve my coding skill, and then try to resolve the bugs existing in my meta-heuristic.
Okay.
Yeah, I think only these two suggestions that I could propose. Yeah.
Okay, very nice, very nice. Thank you for sharing your experience. Well, anyway, so I think it's already been late in Manila. Also, I think in Taiwan. So I guess thank you very much, Dr. Panca, for your sharing today. And yeah, see you again in another occasion. So I think, yeah, let's give big applause for Dr. Panca.
Thank you, Dr. Wira.
Okay.
Thank
So
you,
let's
everyone.
end the session. Thank you very much, everyone, for attending today's session. Okay. Good night. Bye
Good
bye.
night. Bye-bye.
Thank you.